So maybe you can wait a couple of minutes. I think he's coming in a minute. And then, but if you already have some questions, I can already pass to you the microphone. You just raise your hand, and I have two microphones, one for the speaker, one for the... Okay, Guido's going to use the microphone today.
So the question to Antoine is about, you mentioned as a ground state method, the DMRG, and of course, I mean, that's something that, I mean, has worked super well, I mean, for one-dimensional systems, and I mean, for quasi one-dimensional systems. I mean, what is your view now on sort of, in a way, I mean, it's, yeah, power in real, for the two-dimensional problems? Or, I mean, has there been sort of, I mean, some important developments in recent years in this direction?
Okay, so this is a vast topic, and I'm not a complete expert on all aspects, but what I can tell you is at least some how looking at the problem with complementary methods, both DMRG-like and cluster DMFT-like, have allowed to shed light on what actually is going on in the case of the Fermionic-Hubbard model. So one of the new developments, so of course you're right, DMRG and MPS representations are especially efficient for low-dimensional systems, right? So when it comes to Hubbard models, Fermionic-Hubbard models, more or less we are talking about tubular geometries with open boundary conditions in one direction and periodic in the other. If you do ground state, this is going to be 6 and perhaps 8 sites, and this could be very long, right? But if we are talking about finite temperature results, this is probably restricted to really thin things like 4 sites here and 16 there. So one of the, in my opinion, quite significant development in the field has been the combination of MPS representations and sampling methods that allow to go to finite temperature. And so let me explain briefly how this works. There are 2 ways to do that, but I will describe one, which is called METS, and this stands for minimally entangled, typical thermal state. The way this works is the following. You start from a product state, and you're going to act on this product state with this operator, right? And at each time step of, you evolve this in tau, okay, from 0 to beta over 2. At each step, you actually represent the state as an MPS and implement efficient time evolution algorithms to compute this object. And then what you do is that so this is one METS, one state, and what you do is you sample over those states. Okay? And sampling over these states allow you to reconstruct the thermodynamics of the problem. So now I'm going to try to go a little bit to physics. And this would be the temperature axis at some low doping for the two-dimensional Hubbard model. Okay? So what all DMRG studies, and actually all studies, including single-site DMFT, every more or less every computational methods, T prime equals 0, have agreed upon is that here there is at least a regime where the ground state has stripe order of the type I briefly described before. Now, from the high temperature viewpoint, what we have, and so this stripe order comes with spin ordering at a wave vector which is shifted away from pi pi, okay, which will be something like pi minus delta q pi. okay? Where this delta Q is related to the incommensuration to the envelope of the spin density wave I was describing earlier, and correspondingly charge order at twice delta Q. Okay. On the other hand, all methods like cluster extensions of DMFT have said that as you go down in temperature, what first happens is that you start to grow commensurate spin correlations at pi pi. So there is a correlation length that grows a little bit, not to very large values if we are at strong coupling, but grows a little bit. And for a long time, how these two things match was very unclear. As these spin correlations grow, a pseudogap develops in the excitation spectrum. So here we enter some pseudogap regime. So until a few years ago, this was the sort of cluster DMFT explanation of the pseudogap. And on the other hand, the MRG studies will tell you there are stripes, okay? And there was not too much, this was two different points of view on the system. What has happened recently is that now we understand how these two things connect. Not in all details, but at least qualitatively. And the way this works is the following thing. So we have a paper using METS, which involves Steve White. The hero is Alex Vitek, who was a postdoc at CCQ, Steve White and Miles Studenmeyer and myself. And what we see is the following thing. So it is admittedly on small tubes, okay, small diameters. But what we see is the following. If we follow as a function of temperature, the spin structure factor at pi pi and the spin structure factor at pi minus delta Q pi, right? So let me call this SAF and SDW, okay? Just for a notational point of view. So what we see is that indeed SAF grows and then goes down like that. And the onset of this thing, which of course it's a crossover, you can negotiate how to define it, defines the pseudogap. So this is exactly what cluster DMFT is saying. On the other hand, the SDW structure factor is doing nothing here, and here it starts growing and overcomes this.
Oh, okay. Sorry.
And then at the same time, the charge ordering, now I can also plot the charge structure factor at this wave vector, or at twice this wave vector, and it grows at the same time.
Oh, okay.
Okay? So now what this is saying is that as we lower temperature, there is a temperature scale T star at which the magnetic correlations start growing. And then eventually, the incommensurate correlations take over, and at the same time, some charge correlations start appearing. Okay? So this is saying that the pseudogap is driven by the growth of spin correlations, and eventually, the pseudogap state evolves into a striped ordered state, which becomes long-range order at zero temperature.
So the ratio between the T star and sort of where this other increases above it sort of depends on doping.
So the detailed doping dependence has not been done, but at low doping, this is about, at U equal 8 and low doping, this is maybe 1/8 doping, this is about 0.1 times hopping, something like this, 0.05 to 0.1, and this is much higher. This is like 0.25 times T, okay? And just to finish the story, this picture, we've done recently with Riccardo Rossi and Fedor Simkovic and Michel Ferrero, a study using the third technique I was describing, namely seeded diagrammatic Monte Carlo, which Felix likes. And what we find is that indeed, so this scale is reachable with diagrammatic Monte Carlo. This is an old paper, well, 6 or 7 years old that we did with Wei Wu and coworkers. But now we can also do this at lower and lower temperature. The limit, as I was saying, is about 0.20, 0.070. And we could see by extrapolating to 0 temperature that indeed the regime in the phase diagram where there is a pseudogap matches the regime in which in the ground state there is stripe order. So this is the first answer. This is a paper which is going to be published in Science rather soon, which is answering the question, what is the incipient ground state that you reach when cooling down the pseudogap state? And at least 20 prime equals 0, our answer is that intrinsically this pseudogap state is unstable to stripe ordering. Now there are still open questions, since this is a conference about open questions. On these geometries, this is all crossovers. In full finite, two-dimensional infinite system, we expect only spin Lagrange order to only exist at t equals 0 because of Mermin-Wagner. But of course, the charge density wave order breaks a discrete symmetry. And so there should be here a phase transition at finite temperature into a charge ordered state before the spins fully order. And we've seen this from still a fourth numerical method with Shiwei Zhang and coworkers, but the nature, the universality class of this phase transition is still a widely open problem, actually. Okay, that was a very long answer, but it was supposed to be part of my lecture this morning.
Okay, so maybe you keep this one, because I don't know if somebody else is going to ask when I get that one.
Maybe just a follow-up on this. I understood this morning that you said that for the organic crystals, the pseudogap hardly exists or only a tiny part. And I also understood that actually it's more clearly modeled by Fermi-Hubbard, by nature. So can you comment to, let's say, why in this?
Yes, yes, I can do that. So first of all, it's not the same lattice. Okay, so the organic superconductors have a pretty, are on a different lattice. What can I erase? Tillman, do you mind if I erase some of these equations? So A, it's not the same lattice. The lattice of the organic superconductors are some anisotropic triangular with T prime only. You can think of it as a square lattice, but with T prime only in one direction, so it's much more frustrated. And secondly, this is not doped. This is one particle per site, right? Studied as a function of pressure. So it's really not the same animal, right? Again, I don't want to claim that there is no pseudogap physics in this system, but what experiments are telling you is that there is a superconducting phase. This is pressure. This is a metal insulator transition. There is a Fermi liquid coherence scale. And perhaps here, very close to the metal insulator transition, the metal has a small, perhaps here there is a small region of pseudogap. But perhaps the most striking thing is that these materials do not have the strange metal regime of the cuprates. Below this scale, the resistivity is T square. So now the fact that this model can have a superconducting ground state, I would say is not established to the same level of rigor than the very detailed recent studies on square lattice Hubbard. But if you do, we recently have a paper on this, if you do, and André-Marie Tremblay in Sherbrooke has done a lot on that in past years. If you do cluster DMFT studies on this sort of lattice, you do find indeed a superconducting ground state of D-wave symmetry.
So, any more questions? So maybe I'll have a follow-up because I asked something similar during your talk. So the symmetry of the order parameter in those systems, you said that it was not, of course, standard S kind of stuff. There's some anisotropy, but now you mentioned that it's potentially D-wave. But
a theory, okay, the theoretical calculations that several groups have been doing yield a D-wave superconducting state.
Yeah.
Experimentally, I don't think this issue is completely settled. There are several experiments that you can do on cuprates that you cannot do on these systems. Most notably, you cannot do ARPS because these are plastics, basically. They melt when you put light on them. Well, they are degraded, let's say. So there is no ARPS information, so the variation of the superconducting gap on the Fermi surface is not really known. One can do quantum oscillations. I mean, D-wave is certainly consistent with many of the experiments, but I don't think that the issue is settled.
Okay, so but at least they have some evidence thermodynamically at low temperatures. There's some power laws that are consistent with D-wave nodes.
Yes, I think it's mostly consistent with D-wave, but whether it's D-wave or F-wave or G-wave, I don't think this is completely settled.
No, but between D and F, it's a bit. There's an easier experiment you can do to distinguish between that. Yeah. Okay. Mm. Okay. So yes.
Yeah, thank you. So since there are no questions, I allow myself just a small comment. So as Antoine said, in the computational methods, it's important to use some physical insight. And actually, so by lack of time, Antoine only presented the simple expansion in powers of u. But actually, there is an infinite number of possible expansions that one can do. And that's actually what we and other people are doing. So the simple expansion in powers of u, as far as I know, it never works in practice. So the minimum thing is to expand on top of mean field. So in other words, to shift the chemical potential by u, by the Hartree term. And then already it's not an expansion in powers of u anymore. And then there are many other options. So for example, using ladder diagrams, that's what we did for the unitary Fermi gas. Or one can expand on top of BCS mean field, which is itself non-perturbative in U. And for the electron gas, there is a screening which is taken into account, and so on. So yeah, just a small comment.
Yeah, I know, maybe I can elaborate on this. So of course I was very sketchy. So there are many, many flavors of diagrammatic Monte Carlo, which, and in fact, in all the studies that I alluded to, optimizing, even in the non-ordered states, optimizing the starting point proved to be extremely important. That's how we could get the pseudogap for the first time in these kind of schemes. And indeed, if you want to go into the ordered state, you have to start from a symmetry broken state or expand around that. Yeah.
If not, I have a small question for Tillman. So when you talk about quantum critical scaling, I suppose that you mean that this kind of scaling is also what is seen near a quantum critical point. But
yes.
However, here for the unitary Fermi gas, there is no actual quantum criticality with non-trivial critical exponents, right?
Well, many of the exponents are kind of integers or half integers. So this is the kind of scenario put forward by Sachdev and Nikolic some years ago to say, right, at the unitary, or maybe I can draw a quick picture. Yes. Yes, it is scale invariant, and so basically the phase diagram would be in, what is it, chemical potential versus temperature, and somewhere here you have the superfluid state and everything else is normal. Now if you're at 0 temperature at negative chemical potential, you have the vacuum. And here it would be the non-degenerate gas. And the statement is that everything here at unitarity depends only on the ratio of mu and t. So you're basically looking only at angles in the phase diagram. And now the quantum critical regime would usually be expected here, somewhere above the superfluid transition, but still degenerate. And then one can look at the scaling exponents for various observables, and many of them have integer or half integer scaling. I don't know, I mean, there was something like about 3-body losses which might differ, but...
okay, sorry, yeah, go ahead.
No, go ahead. A major point I think here is the following, that I mean, there's a quantum critical point here at 0 density. This is the one which Nikolic and such, they sort of have, in a way, pointed out first. But of course, it's one which is a very simple one. It has, I mean, the only non-trivial, the only anomalous dimension that comes in is sort of the one which comes from the contact operator.
But that again is integer.
So this is the only enormous dimension, and that is something, this is something that, okay, is just 4 instead of 3. So, sorry?
The contact.
The enormous dimension comes, in this case, just from the zero range nature of the interaction. But there is no, if you wish, there is no non-trivial. There are non-trivial exponents, of course, on the if you get sort of close to the superfluid transition. But those are the classical ones that we are not interested, or that's not the focus here. And so in a way, many of the scalings that you get, I mean, you don't get non-trivial power loss. So the issue about, okay, I mean, getting something which, I mean, okay, basically involves non-trivial exponents doesn't arise here because of this. Essentially, it's a consequence just of the zero density nature of this fixed point, and the only non-trivial scaling exponent is the one which is associated with the microscopic interaction, at the fact that we took a zero range, well, one takes the zero range model, but it's not the interactions, or it's not the, that's already the two-body problem, if you wish.
Yes, so maybe I can be a bit less diplomatic, but more explicit. So honestly, I have the impression that insisting on calling it quantum critical is a bit of overselling. Because here, okay, this phase diagram just follows from dimensional analysis, the fact that there is no length scale. I don't see any connection with the quantum critical criticality. And then, yeah, as you just said, in the end, there are no non-trivial critical exponents here. So, I mean.
Yeah, but also if I'm.
You're right. I mean, essentially, sort of the fact that in this range, in this fan, there's this fan above, at finite temperature above this point. But I mean, the fact that, I mean, everything depends on just on these ratios, mu over t or so, is just a consequence of dimensional analysis.
Sure. I agree. I mean, what I wanted to express is that the scattering rate is just some number times kt over h bar, right? So one could also call it the t-linear scaling of the scattering rate without mentioning quantum critical. That's the statement that I wanted to make. And from this quantum critical picture, this follows naturally, because you would say, okay, incoherent excitations decay at a rate that can only be proportional to temperature. What goes in addition is that this prefactor here doesn't really depend on density anymore, right? That is the perhaps non-trivial statement, right? Anything dimensionally, this is always, can always be expressed as something times this, but that the fact that the prefactor does not depend on density is the non-trivial statement.
Yeah, I agree. So this is a not.
I mean, the prefactor, I mean, okay, it could be zero sort of by some chance or so, but otherwise, I mean, just by dimensional analysis, nothing else can come in the zero density limit.
Yes, but then we're interested in finite temperature. So basically what we care about is like if we go across here, does the prefactor change? And for many quantities it would change, but then say for the bulk scattering rate, it does not, and that is surprising.
Yeah, so just before I agree that this is a non-trivial statement, but my impression that this is not actually it's more non-trivial than saying, oh, it comes from known quantum criticality phenomenology. It's just it's an original result which has nothing to do, I think, with quantum criticality, but it's non-trivial. No?
Mm-hmm.
Maybe this is becoming a philosophical discussion to some extent, but can I argue? I don't know, I haven't thought about this problem too much, but could I argue that actually the prefactor here is actually a fixed point property, and the fixed point being the zero density fixed point? Well, it's set by the fixed point property, so it cannot depend on anything. I mean, perhaps what you is the debate that this is indeed a quantum critical point which has all the nice properties of quantum critical point, namely scale invariant, etc., just happens to have trivial exponents, good for you, you know, but that you can deduce many interesting results just from the usual scaling that applies at quantum critical points, and with the bonus that you have mean-field exponents, good. There are other examples in life of.
So the famous eta over S story, I mean, Subier was quite annoyed that he didn't sort of predict that, because he said, oh, it's just an amplitude ratio.
Yeah, okay, so.
I mean, you know, eta vanishes and S vanishes, and I mean, the amplitude ratio is universal.
Okay, so I think there is no contradiction in the room, right? This is just saying that this critical point is especially simple.
I think there's one more aspect to it, and so for many things like eta over S, if you now change the angle, like going from very degenerate to less degenerate, the prefactor would change. Right, so there is still the dependence on the angle. This is zero density, but if you are at finite density, well, your distribution function change everything, so that affects the prefactor here. So this is, in general, a function of beta mu. And for most quantities, okay, this is say, in a ballpark, but it's something order 1, but it's not really constant. And so what we were surprised to find is that for the bulk viscosity, this is actually very much constant in a wide range. No, it doesn't follow from quantum criticality, because we say the shear viscosity is very different, right? That changes as you go across here.
I mean, the angle dependence effectively sort of, I mean, tells you that, I mean, you go out of the critical range.
In different directions, yeah.
I mean, that's a span. So, I mean, you have to, I mean, if you want sort of to get the universal sort of ratios or so, you have to, you approach this quantum critical point from above. And I mean, the closer you get, sort of, I mean, the smaller this range is, and then it's fixed. The number is sort of,
Right.
I mean, ideally you just sort of go along the line mu equals 0 vertically down.
But that, say, if you draw the phase diagram differently as versus T over TF, then the mu equals 0 would be just one particular temperature of around 0.6, right? So in this picture, if you say only straight above is really the quantum critical, then you would only live on one particular point in the phase diagram, and that sounds quite restrictive. Yeah. Yes, I mean, in the sense of such that you get one universal number if you go right here. And if you change parameters, you get different numbers.
But physically, there is nothing special about doing it.
No, absolutely not. It's just choosing one particular angle of going down.
trivial. Namely, it's either a weakly interacting Bose gas or a weakly interacting Fermi gas with the BCS instability. However, if you are at the right at unitarity and the system remains a strong coupling problem down to zero density. So I think the point is special. I mean, as such, they've really realized that. I mean,
any more questions? Maybe you can help. We could switch to swimming. I have a question for Yvonne because perhaps briefly. I'm curious about the last piece. Could you say a little bit in your presentation? There was point number 3 you wanted to make. So the question I have for you, what are the open questions that you said that need microscopic theory from the many-body point of view? I don't think you got to that point. Could you say a few words maybe about that?
The part 3?
Yeah, I think you went only to 2. I don't know what you're going to say on 3. But
okay. Well, to be short, so measure thermodynamic properties, like the equation, or calculate or measure like the equation of state. Determine also parameters that enter in effective theories. So, of course, hydrodynamics, but also, for example, in what I presented in part 2, the little gamma. Can we calculate or measure this curvature parameter? So this I mentioned already in the lecture.
But you mean unitarity only or in general? Because
in general.
There's some experiments already, like for Henri-Moritz experiments for the gamma.
Right, yes.
In principle, they can extract that. I don't know.
Yes, so Henri-Moritz has measured values of little gamma. But the issue is to know if those measurements are extremely precise, because there are several problems. First, this little gamma is a zero temperature property, and the experiments are at rather high temperature. It's 0.13 TF or 0.8 TC. And then if you do a little estimation on a piece of paper, you find that the thermal effect on the acoustic branch will change a lot the curvature. And there is another problem, is that this little gamma is a low Q property, right? So you have to measure the dispersion relation at low Q. And Henri-Moritz actually is rather making a cubic fit over a broad Q interval. So we are not sure, for example, that there would be no change of convexity of the branch over that interval. Maybe over some piece of the interval it's convex, and then on the other piece it's concave. And then when you make a fit, you take an average and you get the wrong answer. Okay. So I think there is space for more precise measurements. And for the theory, little gamma was calculated only with a Gaussian approximation or the RPA. They give the same value. So we don't know how accurate this is. Anyway, the theories predict that in the unitary limit, the little gamma is positive. So the branch is convex. And Henri-Moritz finds that at the unitary limit, the branch is concave. So there is a disagreement. Okay. Another thing that to complete, the effective low energy theories cannot describe modes at energies comparable to the binding energy of a pair. And actually, I think this is an interesting situation because you don't have that in bosons. Here we have composite bosons. We can break them. There is a broken pair continuum. And some theories predict that there is a X mode, so a collective mode branch in that continuum. So doing an accurate calculation is not easy. And as far as I know, there is no measurement at all in any system. So, I mean, working on this X branch, I think is interesting.
Okay.
Okay, we'll stop there. Thank you.
So, any more questions? Yeah, Tillman. Still take this one.
So, Antoine, you mentioned the T-linear resistivity in the cuprates. So what's the explanation for that? Because over the years I have seen so many, they converge, or what is the status?
So indeed, I skipped this under the rug. So what should I say on this? For many, many years, people have tried to find, since we were into quantum critical points of models such as, many of the microscopic models we talked about, that would possess this property. And I think it is reasonably fair to say that up to now, without disorder, there is no clear example where this has been established. So the new fashion in the field has been to invoke the possibility that actually disorder is essential to get T-linear behavior over an extended range. And to some extent, this has its roots into the Sage-Deffier model. So, as you know, Sage-Deffier, back in 1995, is basically an Edwards-Anderson model of a spin glass with random Gij, and it happens to have a spectrum of excitations. Okay, so Sage-Deffier. There was no K at that time. It's basically just the Heisenberg model, even on a fully connected lattice, actually, with random Gij. So typical spin glass model, right? And so you would expect this model to have a spin glass phase, right? But in fact, what Sage-Deffier showed is that if you extend the spin from an SU2, a representation of SU2 to a representation of SUM in large M, the quantum fluctuations destroy the spin glass phase, and this model actually is a spin liquid, right, with spin dynamics, which is actually chi double prime of omega equal constant for omega larger than t and omega over t for omega smaller than t, which is exactly what has been proposed phenomenologically as the marginal Fermi liquid to explain some of the phenomenology of the strange metal. Okay, however, this is purely a model of spin. So a little bit later, in 1999, Olivier Parcollet and myself actually introduced mobile charge carrier in this system. So we promoted this system to, say, a TJ model, right? Where the particles can now hop with some projector here, right? And what we showed, I'm doing a little history here to explain the train of thought in this field. What we showed, still in the large M limit, so here you have, so this is now doping, which we can introduce thanks to this TJ extension. Here we have the Sage-Deffier spin liquid. And what we showed is that this term at 0 temperature is a relevant perturbation which immediately stabilizes a Fermi liquid. So in fancy modern terminology, people call this the SYK2 perturbation. But you can just think of it as we did it back in the day as a hopping. But that, however, there was a crossover scale here, above which you recover exactly what you have here, namely linear in temperature resistivity, okay? But linear in temperature resistivity in a regime in which the resistivity is large as compared to the quantum of resistivity, to what's called the Mottio-Farigel limit. So this is not a theory of a strange metal. This is a theory of a bad metal. it's quite important to understand the difference between these two things. The mystery of strange metals is that you can get T-linear resistivity in regimes where the mean free path is large. This is a theory of T-linear resistivity in regimes where the mean free path is comparable to the lattice spacing, which is more appropriately called bad metal, and there are many mechanisms for that. Okay, but this is M goes to infinity, right? And what has been realized recently in the past 5 years or so is that if you now look back into the true system, SU2, this business that we had with Poincaré and myself is completely changed. What you get here is not a Sage-Diffie liquid, it's actually a spin glass, as you would expect, because now we have just a random coupling Heisenberg model. A Fermi liquid here, indeed, and here a quantum critical regime, which is the melting of this metallic spin glass, in which, indeed, you can have T-linear resistivity down to T equals 0. And so there are several papers that have done that. There is a paper by Subir, Sage-Def, myself, and a bunch of other authors in like 6-7 years ago. And then some more numerical papers involving Philippe Dumitrescu and recently also Nikita Kavokin. And so this is indeed a proper theory of T-linear resistivity, but you see that it requires the introduction of randomness. And this has opened, I mean, this and other works have opened a whole field of research in which people have now moved. So you could say, okay, this sort of random Heisenberg model with random J of arbitrary sign that has no physical relevance to cuprates, and probably to some extent you would be right. But this has been recently generalized to what's called random Yukawa models. And here, one of the key names is Avishkar Patel, with Subir Sage-Def and co-workers, and also Jörg Schmalian. And basically the idea now is to change a bit this and to have a coupling between your fermions and a spin mode, which now can be the mode of an antiferromagnetic spin density wave, with a coupling constant, let's say GIJK, okay, which is random. And there is a nice paper by Avishkar Patel in Science that you may have seen a couple of years ago that actually provide the theory of T-linear resistivity in this sort of model. So to cut a long story short, there are models in which one can now convincingly essentially establish that there is T-linear resistivity down to T equals 0, so appropriately called strange metals now, but at the expense of invoking disorder. Disorder not as just random impurity scattering, but actually disorder in the interaction strength. And now whether this indeed is phenomenologically or microscopically justified, and indeed it is true that all these materials in which when C is T-linear resistivity down to low T is intrinsically a property for which disorder is important, it is a completely open problem. And I have myself mixed feelings about it. Sometimes I think yes, sometimes no. So that's an open problem. There is no real microscopic justification of this to this day.
So basically, the random interaction you need is like the Sage-Def term.
Or I mean, they are basically either of this garden variety here, but that's almost certainly not physical, say for cuprates or anything, because this requires ferromagnetic and antiferromagnetic interactions. So, these systems are dominantly antiferromagnetic. Or you can make this thing better by having this type of interaction in which the fermions couple to the slow mode of an antiferromagnetic spin density wave.
These are space indices, I
Yes, but with some randomness. Well, with some randomness. So to be more precise, we have a G which depends on R, and some. No. These are internal indices. Okay, these are internal indices of the system, and you need a spatially random interaction. This is more complicated than this. There are different types of random terms, but that's the general spirit.
So any more questions? So call like a once and twice and 3 times? No? Okay, so then we can stop 5 minutes before the end of the session. Thank the speakers again. Thanks everybody for asking questions, and enjoy the evening, I guess. Thank you very much.